The artificial intelligence revolution is supposedly a frictionless cloud of infinite code, but the cloud is a lie. It turns out the most advanced software in human history is violently physical. It is made of concrete, copper, and thousands of gallons of boiling oil. Right now, Silicon Valley has $1 trillion problem. They have the capital, they have the chips, but half of these shiny new gigawatt data centers might just end up as very expensive brick buildings. Because the ultimate bottleneck throttling the AI boom isn't a quantum processor, it's a 19th century invention called large power transformer. And if you'd like to order one today, plug in your $1 billion server farm. Please take your ticket. Your delivery date is sometime in 2030. These 400-ton steel behemoths are the only thing standing between the future of intelligence and a total blackout. This is the story of how the tech world is currently being held hostage by a giant block of metal, and a handful of companies quietly making a fortune from the chaos. Every time you ask an AI a question, it uses up to 10 times the power of a standard Google search. To train these massive language models, companies are buying hundreds of thousands of GPUs, but GPUs are hungry. A legacy data center rack, the kind that runs most of the internet today, draws about 5 to 10 kilowatts of power. The new NVIDIA Blackwell racks, they draw 120 kilowatts. The upcoming Rubin Ultra racks will pull 600 kilowatts. At that density, standard air conditioning physically stops working. You have to pump chilled liquid directly into the chips to keep them from melting through the floor. You are effectively pumping equivalent of a small city's power grid into a single building. You can't exactly plug a gigawatt data center into a surge protector and hope for the best. You need to pull high voltage electricity straight from the transmission grid. And to step that extreme 345 kilowatt power down so it doesn't instantly vaporize your $1 billion server farm, you need a large power transformer. These behemoths can weigh up to 900 metric tons. They are filled with miles of hand-wound copper wire and tens of thousands of gallons of highly refined mineral oil. You can't just mass-produce these on an automated assembly line. The construction requires painstaking manual craftsmanship. The cellulose insulation paper alone has to be baked in a vacuum chamber for weeks to remove a single drop of moisture. At ultra-high voltages, one drop of water equals a catastrophic explosion. Because they are so difficult to build, the lead times have gone parabolic. Before 2020, ordering a large transformer took about a year. Today, lead times have inflated up to 600%. A generator setup transformer will now take 144 weeks to deliver. For the biggest units, you are waiting over 4 years. This has created a financial nightmare known as stranded capex. Imagine spending $2 billion to build state-of-the-art AI campus. The building is done. The servers are ready, but it sits completely dark, depreciating by hundreds of millions of dollars a year because you're waiting on a metal box. So why can't we just build more transformer factories? Because the bottleneck isn't a factory. It's buried deep inside the core of the transformer itself. It's a specialized metal called grain-oriented electrical steel, or GOES, and we are running out of it. This steel isn't the steel you use to build a bridge. GOES is practically a subatomic crystal lattice. Metallurgists have to roll the steel down to fractions of a millimeter, carefully applying heat and tension so the iron atoms align perfectly in what is called ghost texture. This creates a frictionless highway for magnetic fields. If the atoms are misaligned, energy is lost as heat and the transformer becomes wildly inefficient. GOES is so incredibly difficult to make that a new factory costs over $1 billion and takes 5 years to build. Because of this, global population is locked in a tight oligopoly of just few companies capped at around 4 million tons a year. This is where it gets geopolitical. Today, China controls 56% of global GOES market. The United States? It has exactly one factory left capable of producing this material, the Cleveland Cliffs Butler Works plant in Pennsylvania. Cleveland Cliffs is currently spending $150 million to convert an old tin-plate mill in West Virginia into a new transformer plant, just to help meet demand. But, broadly speaking, if one domestic steel plant hiccups, the expansion of the American power grid grinds to a halt. You can't agile sprint your way out of a metallurgy shortage, but let's say you wait 4 years, your transformer is finally built. Now you have another problem. FedEx doesn't offer overnight shipping for a 900-ton box. You have to move it. To move a large power transformer, you need a Schnabel car. These are custom-built multi-axle rail cars that literally split in half and use the transformer itself as the center bridge of the train to distribute the weight. There are fewer than 100 of these specialized cars in the entire world. The largest one can carry over 1,000,000 pounds. They move at an agonizing 15 miles per hour. The routes have to be planned months in advance just to ensure bridges don't collapse and the train doesn't derail on a tight curve. The logistics alone can add millions to the cost. Faced with 4-year delays and a grid that simply cannot support them, Silicon Valley is panicking. If they can't get the transformers to connect to the grid, their solution is to simply bypass the grid entirely. They are buying their own power plants. In a move that shocked the energy sector, Microsoft signed a 20-year, $16 billion deal to secure the entire output of Pennsylvania nuclear power plant to feed its AI ambitions. That plant? 3 Mile Island. Yes, that 3 Mile Island. Google is following suit, partnering to build a fleet of small modular reactors. They are attempting to plug gigawatt AI clusters directly into nuclear generation just to avoid the transformer supply chain. It is desperate, brilliant, and incredibly expensive workaround. We spent the last 3 decades believing we were ascending into the digital ether, but the foundation of the digital world is heavy. It requires miners, train conductors, and steel workers. The smartest algorithms in the world are currently waiting in line for a piece of 19th century Pennsylvania steel. The future isn't just about who can write the best code, it's about who can forge the steel to power it.